Hi, I am Sanjay Patel. In this video, we are going to solve some special problems on Leibniz theorem. Let us start with the first one. If In denotes the nth derivative dn by dx raised to n of the function x raised to n into log x, the base is obvious, then prove that In is equal to n times In minus 1 plus n minus 1 factorial and hence derive that In is equal to n factorial into log x plus 1 plus 1 by 2 plus 1 by 3 and so on up to 1 by n for every n belongs to n. Okay, so let us solve this. So solution, here I start with this symbol In, which is defined as the nth derivative of x raised to n into log x. Okay, this I can write as say dn minus 1 by dx raised to n minus 1 of d by dx of x raised to n into log x. X raised to n into log x. Okay. And you know that if you take the first derivative of some function, then to find the nth derivative, you need to find n minus 1th derivative of that first derivative. So then you will get the nth derivative of the required function. Okay. So this is equal to dn minus 1 by dx raised to n minus 1 of this derivative we will find using u into v root. So I can write it as derivative of x raised to n as n into x raised to n minus 1 into log x as it is plus x raised to n as it is, and derivative of log x is 1 upon x. Okay. Now separating this, we can rewrite it as this is equal to n minus 1th derivative of this plus n minus 1th derivative of this. So I can write it as n into dn minus 1 by dx raised to n minus 1 of x raised to n minus 1 into log x. As n is constant in multiplication, we have written it outside of the derivative sign. And then dn minus 1 by dx raised to n minus 1 of this. And this thing is x raised to n minus 1. Okay. Now just go back to this symbol. In means dn by dx raised to n x raised to n log x. So for example, if you have n equal to 2, I2 means d2 by dx square of x square into log x. So In minus 1, if you put n equal to n minus 1, In minus 1 is dn minus 1 by dx raised to n minus 1 of x raised to n into x raised to n minus 1 into log x. So this term I can replace using the In minus 1. This derivative I can write as In minus 1 plus, now x raised to n minus 1 is a polynomial of degree n minus 1, and its n minus 1th derivative is constant, which is given by n minus 1 factorial. For example, you know, if you have y is equal to x cube, then its third derivative d3y by dx cube is nothing but 3 factorial. So in general, nth derivative of x raised to n is n factorial. Fine. And the left hand side here is in. So we have proved that first relation in is equal to n into in minus 1 plus n minus 1 factorial. Now let us divide both the sides by n factorial. Divide both the sides of this recursive relation by n factorial. So what we get here is in upon n factorial is equal to n upon n factorial. That gives us n minus 1 factorial. N upon n factorial is 1 upon n minus 1 factorial, and here we get n minus 1 factorial upon n factorial, that is 1 upon n. You know, 8 factorial upon 9 factorial is 1 upon 9, something like that. If we have 8 factorial upon 9 factorial, that means this is 1, 2, 3 up to 8 and this is 1, 2, 3 up to 9. So everything will be cancelled and we get 1 upon 9. So n minus 1 factorial upon n factorial gives you 1 upon n. Okay, and this is true for every n is equal to 1, 2, 3 and so on. And let me call this as result number 1. Okay. Now let us put n equal to 1, 2, 3 and so on in this equation 1 and see what happens. Taking n is equal to 1, 2, 3 and so on, we get for n equal to 1, I have I1 upon 1 factorial is equal to I0 upon 0 factorial plus 1 upon 1. Then for n equal to 2, I will get, this is for n is equal to 1. Then for n is equal to 2, I2 upon 2 factorial is equal to I1 upon 1 factorial plus 1 upon 2. This is for n is equal to 2. For 3, similarly, we can write I2 upon 2 factorial plus 1 upon 3 for n is equal to 3 and so on. And we want to write now this type of equations for 1, 2, 3 up to n. So the last step I would like to write is in upon n factorial is equal to in minus 1 upon n minus 1 factorial plus 1 upon n. Okay, now we add all these equations. Okay, so let me write this adding the above equations, we get, if we add all this, then the left hand side the sum of all these terms and right hand side the sum of all these terms plus 1, 1 by 2 plus 1 by 3 up to 1 by n. And you can see that this will be cancelled in that sum. So I will write directly this and this will be cancelled. When you add this and this will be cancelled. So likewise this previous term and this will be cancelled. So what is left when you add all this is only this in upon n factorial, this term, and in the left hand side and the right hand side, what is left is I0 upon 0 factorial and all these numbers 1, 1 by 2, 1 by 3 and so on. So that we can write as in upon n factorial is equal to I0 upon 0 factorial, that is 1 plus 1 plus 1 by 2 plus 1 by 3 plus and so on up to 1 by n. Okay, and this implies I can write this as in is equal to n factorial into I0 plus 1 plus 1 by 2 up to 1 by 3. So it only remains to check what is I0 here. we have defined in is equal to nth derivative. In is equal to dn by dx raised to n of x raised to n into log x. So we have I0 means the zeroth derivative is nothing but the function x raised to 0 into log x. Okay, and it is simply log x only. D0 means zeroth derivative, but that we consider as the function only. I0 means the given function. I1 is the first derivative of that function. I2 is the second derivative of this function, and so on. So this gives us from this last equation that in is equal to n factorial into log x plus 1 plus 1 by 2 plus 1 by 3 and so on up to 1 by n. So this completes the solution of this problem. Let us go to the next one. That is problem number 2. Say prove that dn plus 1 by dx raised to n plus 1 of x raised to n into log x raised to n into log x is n factorial upon x. Okay, this result actually follows from our previous problem. So let us prove it. So first you have to write down the solution of this. We'll write that we know that in is equal to dn by dx raised to n of x raised to n into log x implies what we can write, this is equal to, we have proved that this is equal to n factorial into log x plus 1 plus 1 by 2 up to 1 by n. Okay, so this is the nth derivative of x raised to n into log x. What we need to find is the n plus 1th derivative of the same function x raised to n into log x. So therefore I can say dn plus 1 by dx raised to n plus 1 of x raised to n into log x is given by d by dx, means one more derivative of the nth derivative of the same function. So I am writing in this way. This means the nth derivative of x raised to n into log x, and then if you take one more derivative d by dx, you will get the n plus 1th derivative. But we have already obtained this nth derivative here in the previous problem, so I will write the value of that derivative here. So this implies what we'll get here is this is equal to d by dx of log x plus, we'll get d by dx of this function, that is n factorial into log x plus 1 plus 1 by 2 plus and so on plus 1 by n. We have to just differentiate this thing. N factorial is constant, so that will remain as it is. Derivative of log x is 1 upon x, and derivative of all other terms 1, 1 by 2 and so on up to 1 upon n, all will be 0. So what we are left with is only n factorial upon x, which was the required result. So this is proved. So very simple problem which follows from the main problem. In is equal to dn by dx raised to n of x raised to n into log x. Okay, now let us go to the next one. Problem number 3. If y is equal to log of 1 plus x upon 1 plus x, then prove that then prove that yn 0 plus n times yn 0 plus n times yn minus 1 0, yn minus 1 of 0 is equal to minus 1 raised to n minus 1 into n minus 1 factorial. Okay, and hence show that yn 0 is given by minus 1 raised to n plus 1 into n factorial into 1 plus 1 by 2 plus 1 by 3 plus 1 upon n. Let us prove. So first of all, we have the given function y is equal to log of 1 plus x upon 1 plus x. Our final aim is to find the nth derivative and obtain this relation as well as the nth derivative value at 0. So there are two things to be proved in this problem. So first of all, I want to write this 1 plus x in the left hand side. So let us taking the cross multiplication. 1 plus x into y is equal to log of 1 plus x. Okay. Now we take nth derivative in this. So let me write this way. Taking nth derivative on both the sides. So what we are writing here is 1 plus x into y, the nth derivative of this product, and nth derivative of the function log of 1 plus x. We have the formula for finding nth derivative of log of 1 plus x. Let me just mention that formula here so that you can understand. We know that y is equal to log of ax plus b, then its nth derivative yn is given by minus 1 raised to n minus 1 into n minus 1 factorial into a raised to n upon ax plus b raised to n. So this is the formula for finding nth derivative of log of ax plus b. Here a is equal to 1 and b is equal to 1. And in the left hand side, we have product of two functions and we want to find its nth derivative. So I will apply the Leibniz theorem for this left hand side function. So the next step will be applying Leibniz theorem for the left hand side. We get nc0, and you know in Leibniz theorem, the function whose derivative becomes 0 after some stage we take as v. So this is a polynomial of degree 1. Its second derivative will be 0. So this I am taking as v and this as u. So nc0, nth derivative of u, that is yn, into the function 1 plus x as it is, plus nc1 into 1 less than this, that is yn minus 1, and the first derivative of 1 plus x, that is simply 1. And the next derivative of this 1 will be 0. So all other terms after the second term onwards will be 0. So we stop here. On the right hand side, log of 1 plus x nth derivative is given by this formula. So we'll write here it is minus 1 raised to n minus 1, n minus 1 factorial, and a is equal to 1, so no need to write this, upon 1 plus x or x plus 1 raised to n. Okay. Simplifying this, nc0 is 1, so I will get 1 plus x into yn, nc1 is n into yn minus 1 is equal to this thing, minus 1 raised to n minus 1 factorial upon 1 plus x raised to n. Okay. Now see that we need yn0, this relation, yn0 plus n times yn minus 1, 0. That means we need to find these two derivatives at x equal to 0. And our last equation involves yn and yn minus 1, both the derivatives. So putting x equal to 0 in this, we'll get the value of those two derivatives at x equal to 0. So taking x is equal to 0, in 1, we get yn 1 plus 0, let me write this way, 1 plus 0, and yn at x equal to 0 means yn 0, plus here putting x equal to 0, we get n times the derivative of y, n minus 1 derivative y at 0, and the right hand side is minus 1 raised to n minus 1 into n minus 1 factorial upon 1 plus 0 raised to n. Okay, so this gives us yn 0 plus n into yn minus 1 0, n minus 1 of 0 is equal to minus 1 raised to n minus 1 into n minus 1 factorial. And this is the first required result in our given problem. So we have proved this yn 0 plus n times yn minus 1 of 0 is equal to this minus 1 raised to n minus 1 into n minus 1 factorial. Now to prove this, let us write the same step, equation number 2, in a different way. What I would like to do first is let us divide this by, say, n factorial. Divide equation 2 by n factorial. So what I will get is yn 0 upon n factorial, and then n upon n factorial gives you n minus 1 factorial for this second term. So you will get yn minus 1 of 0 upon n minus 1 factorial, and here minus 1 raised to n minus 1, n minus 1 factorial upon n factorial. So that gives you yn 0 upon n factorial, okay, plus yn minus 1 0 upon n minus 1 factorial, and this I can write as minus 1 raised to n minus 1 upon n. Okay. Now what I want to do here is let us observe the result. Yes, we want minus 1 raised to n plus 1 here. Okay. So let us multiply this equation by minus 1 raised to n on both the sides. So what I will get is, multiplying this by minus 1 raised to, say, n, we get minus 1 raised to n into yn 0 upon n factorial plus minus 1 raised to n into yn minus 0 upon n minus 1 factorial is equal to, this becomes minus 1 raised to n minus 1 into minus 1 raised to n gives you minus 1 raised to 2n minus 1 upon n. Okay. So minus 1 raised to 2n minus 1, and 2n minus 1 is a odd number. So this is minus 1 only. We don't know what is n, but 2n minus 1 is always odd. So this I can rewrite. The first step I am writing as it is, minus 1 raised to n into yn 0 upon n factorial plus this I want to write in this form. Say I want minus 1 raised to n minus 1 over here. So I multiply and divide by minus 1 raised to minus 1. So let me write this way. minus 1 raised to n minus 1 yn minus 1 0 upon n minus 1 factorial and into say minus 1. So let me write here minus 1. This minus 1 I can write here. Okay, this is minus 1 raised to 1 and minus 1 raised to n minus 1. That makes this as minus 1 raised to n. And this right hand side is minus 1 upon n. Okay, now this is symmetric. Here everywhere the number n is involved. Here everywhere number n minus 1 is involved. And both are similar terms. So let me define, say, let us put say Tn is equal to minus 1 raised to n into yn 0 upon n factorial. So this implies Tn minus 1 is equal to minus 1 raised to n minus 1 into yn minus 1 0 upon n minus 1 factorial. Okay, so using this notation, I can rewrite this equation as this is Tn minus 1 is equal to minus 1 upon n, and let us call this as equation number 3. This is true for n is equal to 1, 2, 3 and so on. So taking n is equal to 1, 2, 3 and so on, we get for n is equal to 1, 2, 3 and so on, say T1 minus T0 is equal to minus 1 upon 1. Okay, then putting n is equal to 2, we get T2 minus T1 is equal to minus 1 upon 2. For n equal to 3, T3 minus T2 is equal to minus 1 upon 3 and so on. And finally, we'll get Tn minus 1 is equal to minus 1 upon n. And now we'll add all these equations, adding this all n equations, the n equations above, we get what happens here is when you add all these equations is this T1 will be cancelled, T2 will be cancelled, and so on. Similar Tn minus 1 and this will be cancelled. So what we are left with is only this term and Tn. So I can write it as Tn minus T0 is equal to minus 1 by 2 minus 1, just a minute, minus 1 by 2 minus 1 by 3. This is the sum of the all terms in the right hand side. Okay, so this implies we get Tn is equal to say T0 minus, or let me write this way, 1 plus 1 by 2 plus 1 by 3 up to 1 by n. Okay, but what is T0? T0 means we have to put n equal to 0 in this. So for n equal to 0, T0 is minus 1 raised to 0, that is 1. Y0 we understand as y, the function y of 0 upon 0 factorial. Let me write it as T0 is equal to minus 1 raised to 0 into y0 of 0 upon 0 factorial. That is nothing but simply y of 0. Minus 1 raised to 0 is 1, 0 factorial is also 1, and y0 means y, and y of 0 means value of the function y at x equal to 0. Now what is the function y? That function y given in the problem is y is equal to this thing, log of 1 plus x upon 1 plus x. So let me write that. So y0 is log of 1 plus 0 upon 1 plus 0, and that is nothing but 0, because log 1 is 0 and denominator is 1 here. So y of 0 is 0. That means t0 value is 0. So we get this thing. Putting this value here in this result number, say 4, in the result number 4, what we get is this. So 4 implies Tn is simply minus 1 plus 1 by 2 plus 1 by 3 up to 1 by n. Now what is Tn? Tn is nothing but minus 1 raised to n into yn of 0 upon n factorial, and that is equal to minus 1 here, 1 plus 1 by 2 up to 1 by n. Okay, multiplying both the sides of this equation by minus 1 raised to n, what we get is here minus 1 raised to n into minus 1 raised to n gives you minus 1 raised to 2n into yn 0. This n factorial I am taking on this side, and here if you multiply by this and let me write n factorial first, n factorial into minus 1 raised to n plus 1 into 1 plus 1 by 2 up to 1 by n. Okay, so this gives the required result. Minus 1 raised to 2n is plus 1, so yn 0 is given by n factorial into minus 1 raised to n plus 1 into 1 plus 1 by 2 plus 1 by 3 up to 1 by n. Hence, this problem is solved. This was the required result, as you can see in this problem. Yn 0 is equal to minus 1 raised to n plus 1 into n factorial into 1 plus 1 by 2 up to 1 by n. Okay, so we'll see some more interesting problems in our next video. There are some special problems which can be solved with the help of Leibniz theorem. Okay, so thank you.